April 15, 1942, London, the Petroleum Warfare Department headquarters. Arthur Clifford Hartley sets down his teacup and stares at the three men across the mahogany conference table. Brigadier Sir Donald Banks, Director General of the department. Sir Arthur Charles Hearn, former director of the Anglo-Iranian Oil Company. George Martin Lees, one of Britain's most eminent geologists. All three are shaking their heads. They have just declared impossible what Hartley's boss, Lord Louis Mountbatten, Chief of Combined Operations, desperately needs: a pipeline across the English Channel. Impossible, Hartley thinks, watching them gather their papers. That's what they said about the Iran pipeline, too. The mathematics are brutal. 70 miles of open water, tidal currents reaching 4 knots, depths exceeding 180 feet in places, and the requirement that makes conventional construction absurd. The entire pipeline must be laid in a single operation, fast enough to outpace both tide and enemy, ideally under cover of a single night. No pipeline of such length has ever been laid under such conditions. Submarine pipelines exist in ports, spanning short distances in calm harbors, but this, across one of the world's most treacherous shipping channels, while enemy aircraft patrol overhead and U-boats prowl below? The expert consensus is clear: infeasible with any known method. Traditional pipeline construction involves welding together short sections, a process measured in weeks or months. The tides alone would destroy such an effort before completion. Even if they could somehow assemble it, any pipeline 6 inches in diameter or larger, the minimum bore needed to move meaningful volumes, would be impossibly heavy to deploy from ships in open water. But Hartley has just returned from Iran, where Anglo-Iranian faced a different impossible problem: moving crude oil through 150 miles of mountainous terrain where conventional pumping stations couldn't be built. The solution had been counterintuitive: use a smaller pipe and dramatically increase the pressure. A 3-inch diameter pipeline running at 1,500 pounds per square inch delivered 100,000 imperial gallons per day, the equivalent of over 20,000 jerrycans that would otherwise require convoy after convoy of vulnerable trucks. The mathematics worked because of a simple principle: when you can't make things bigger, make them stronger and push harder. Mountbatten's requirement is stark. After the Allied invasion of France, still 2 years away but already consuming every hour of planning, the advancing armies will need approximately 800 tons of fuel daily. That's nearly 1 million gallons every day, without interruption, without failure. The alternative is tankers, which the Luftwaffe and U-boats will hunt with ruthless efficiency in the confined waters of the Channel. A single successful attack could cripple the entire invasion. Ships are large, slow, and impossibly visible. They burn fuel getting to France. They require escorts, which burn more fuel. They're vulnerable to weather, to mines, to aircraft, to submarines. Every tanker voyage is a roll of the dice. As the three consultants leave the room, still discussing the impossibility they've just concluded, Hartley remains seated. His mind is not on what cannot be done. It is on something else entirely, something that might work if they're willing to think smaller and pump harder. The insight comes from an unlikely source. Since the 1850s, telegraph companies have laid cables across oceans using massive drums and specialized ships. The technology is proven. The ships exist. Companies like Siemens Brothers have been doing it for nearly a century. They wind copper cable onto enormous drums, steam out to sea, and unspool it continuously onto the ocean floor. What if, instead of copper wire carrying electrical signals, they used lead pipe carrying fuel? On April 15, 1942, Hartley presents his proposal to Geoffrey Lloyd, the Secretary for Petroleum. Not a traditional pipeline, but something resembling a submarine communications cable. A continuous length of flexible pipe, wound on enormous drums that could be unreeled across the channel floor in a single operation. Small diameter to keep weight manageable, extreme pressure to move the necessary volume, multiple lines for redundancy and capacity. Deploy them like telegraph cables, continuously, quickly, from specialized chips that already know how to do this work. The project receives a code name that will become legend: PLUTO, Pipeline Under the Ocean. Some sources later claim it stands for Pipeline Underwater Transportation of Oil. The precise etymology matters less than the reality. Britain is about to attempt the longest submarine pipeline in history, using technology that doesn't yet exist, to solve a logistics problem that could determine whether Allied forces advancing from Normandy beaches stall within sight of Paris or drive all the way to Berlin. This audacious project, born from a single man's vision, would indeed change everything. If you want to see how this moment altered the course of World War II, please hit that like button. It helps us share more stories like this, and subscribe if you haven't already. The journey from Hartley's proposal to the first fuel flowing beneath the channel will take 28 months, require the invention of entirely new engineering techniques, and demand the construction of specialized ships and equipment that exist nowhere in the world. But on this April morning in 1942, none of the obstacles are yet visible, only the opportunity to make the impossible happen, because the alternative, watching an invasion starve for fuel within weeks of landing, is unthinkable. Hartley knows something the experts who just left don't. Impossible is just another engineering parameter to be changed. The origin of Pluto lies in the mathematics of modern warfare. By early 1942, British planners understood that 60% by weight of all invasion supplies would be petroleum products, not ammunition, not food, fuel. Every Sherman tank consumed 150 gallons per 100 miles. Every C-47 burned 150 gallons hourly. The planned invasion would land hundreds of thousands of troops supported by thousands of vehicles. The cumulative appetite was staggering. Initial plans called for packaged fuel, 20-liter jerrycans and 44-gallon drums. 20 million jerrycans would be required. But jerrycans had to be loaded onto ships, transported across the channel, unloaded onto congested beaches, loaded onto trucks, and driven to forward units. The process was slow, labor-intensive, and vulnerable at every stage. Tanker ships offered an alternative, but tankers were large, slow targets in confined channel waters. German bombers could find them. U-boats could sink them. Channel weather could ground them for days. A single storm could starve the invasion of fuel. This was the impossible problem Lord Louis Mountbatten confronted in early April 1942. As Chief of Combined Operations, Mountbatten knew that logistics could kill an operation as surely as enemy fire. On April 2, 1942, he summoned Geoffrey Lloyd, Secretary for Petroleum, and asked a question that seemed absurd. Could an oil pipeline be laid across the English Channel? Lloyd consulted his experts. Their response was unanimous: no. Conventional pipeline construction involved welding together 40-foot sections, requiring stable platforms, precise alignment, and extensive time. Attempting it in open water while fighting tides and weather was technically impossible. But Arthur Clifford Hartley disagreed. The 53-year-old chief engineer of Anglo-Iranian Oil Company had spent decades solving impossible pipeline problems. In Iran, he'd recently built a small-diameter, high-pressure system, a 3-inch pipeline at 1,500 psi, moving 100,000 imperial gallons daily, far more than conventional engineering suggested possible. On April 15, 1942, Hartley presented his proposal: adapt submarine telegraph cable technology. Since the 1850s, telegraph companies had laid cables across oceans by winding them on massive drums. Replace the copper core with a lead pipe. Wrap it in steel tape and armoring. Wind it onto drums for deployment. Use multiple small lines instead of one large pipe. Pump at extreme pressure to move the necessary volume. The brilliance: a continuous cable laid in a single operation avoided underwater welding, small diameter kept weight manageable, high pressure compensated for reduced bore, multiple lines provided redundancy. Lloyd approved research on April 18, 1942. The project, codenamed PLUTO, received highest priority classification. By May 1942, Siemens Brothers and Anglo-Iranian began prototype development. The first test on May 10, 1942, across the River Medway failed within 48 hours, lead extruded through gaps in the steel reinforcement. The solution: increase steel tape from 2 layers to 4. On August 14, 1942, full-scale production began. The HAIS cable, Hartley Anglo-Iranian Siemens, consisted of a 3-inch lead pipe surrounded by asphalt, paper tape, 4 steel tapes, wire armoring, jute, and camouflaged canvas. Each mile weighed 46 tons. December 29, 1942 brought the crucial test. HMS Holdfast laid 30 miles across the Bristol Channel during winter storms, winds exceeding 30 knots, heavy seas, poor visibility. The lay succeeded. Shore connections were completed in March 1943. Then came pumping. Starting at 750 psi, engineers pushed to 1,500 psi. The cable held and delivered 56,000 imperial gallons daily, proving the concept worked. But capacity was insufficient. A single 3-inch line wasn't enough for a major invasion. The solution required parallel development of a second technology: Hamill pipe. By early 1943, Pluto split into 2 parallel tracks. The HAIS cable worked but lacked capacity. Delivering 1,000,000 gallons daily would require 18 cables. Theoretically possible, but operationally daunting. The solution came from B.J. Ellis and Major A.E. Hammock: rigid steel pipe wound onto enormous drums. Conventional wisdom said this was impossible. Steel pipe would kink. But they calculated that 3-inch pipe with 0.188-inch walls possessed enough elasticity to coil onto 30-foot drums without permanent deformation. The Hamill pipe, combining Hammock and Ellis, could be manufactured far faster than cable. The deployment system was HMS Conundrum, a drum 30 feet in diameter resembling an enormous cotton reel. 6 were constructed at 30,000 pounds each, empty weight 250 tons. Fully loaded with 90 miles of pipe, 1,600 tons displacement. HMS Persephone, a converted barge, carried the Conundrum and deployed the pipe as it rotated from forward motion. Initial Hamill tests across the Solent succeeded. The pipe laid smoothly and delivered greater volume than HAIS cable. The decision: deploy both technologies. HAIS would form the backbone, reliable and flexible. Hamill would provide additional capacity. Site selection began in spring 1943. The Isle of Wight, particularly Sandown and Shanklin, offered 70 miles to Cherbourg. Pumping stations were built into the Royal Hotel ruins and civilian buildings for disguise. The second site was Dungeness in Kent, only 31 miles to Boulogne, but requiring 71 miles of pipeline extension from the national system. Security demanded ingenious deception. At Dungeness, a major pumping station was disguised as a gravel pit with fake sorting equipment. Another resembled a bungalow. Neighbors appeared to be more bungalows, garages, even an ice cream shop. Each was actually a sophisticated pumping facility capable of 1,500 psi. Construction occurred at night. Equipment arrived under tarpaulins. The cover story varied: military stores or fuel depots for local defense. No one mentioned pipelines or France. By summer 1943, the inland network was complete. The government pipeline and storage system had been extended to connect West Coast ports with southern staging areas, 990 miles total, one of the world's most extensive pipeline systems, all built in under 3 years. The operational concept was elegant. American and British tankers arriving at Liverpool or Bristol would pump fuel into the GPSS. It would flow south through buried pipe to coastal storage. Specialized pumps would boost pressure to 1,500 psi and force fuel across the channel. French receiving stations would reduce pressure and distribute fuel to forward units. The beauty? Invisibility. German reconnaissance would see nothing. No tankers, no convoys, no vulnerable dumps. The Allies' most critical supply line would flow silently 180 feet below the surface while German intelligence searched frantically. Naval support required specialized vessels. HMS Holdfast, HMS Latimer, HMS Sancroft, and HMS Algerian were modified for cable and pipe deployment. By war's end, the Pluto flotilla included over 30 vessels employing more than 1,000 personnel under Captain J.F. Hutchings. By December 1943, the technology worked. Pluto could deliver fuel across the channel in meaningful volumes, but the invasion, postponed from May to June 1944, changed timelines. Intelligence revealed Cherbourg's fortifications were far more extensive than believed. Pluto planners began preparing for longer timelines and more difficult circumstances. The pattern was established: audacious concept, rigorous testing, relentless refinement. By spring 1944, Pluto was steel on the seafloor, pumping stations humming, trained crews ready. It was the invisible artery waiting for its moment. June 6, 1944. D-Day. As Allied forces stormed Normandy beaches, Pluto remained a contingency waiting for Cherbourg's capture. The original schedule called for the port to fall by D+8, June 14th. Reality proved far more difficult. German resistance was ferocious. The port, defended by the 709th Infantry Division with extensive fortifications, didn't fall until June 27th, D+21, 13 days behind schedule. Worse, it was unusable. German engineers had executed demolitions with devastating thoroughness. The harbor was blocked with scuttled ships, cranes were toppled, critical infrastructure was destroyed. This disaster validated Pluto's strategic value. If Cherbourg was this badly damaged, traditional fuel supply chains were impossible. The pipeline suddenly looked not like a supplement, but potentially the only reliable method to deliver fuel in quantity. Through July, American engineers repaired Cherbourg, while Pluto crews prepared deployment. The plan lay Bambi, from Shanklin on the Isle of Wight to Querqueville near Cherbourg. Distance 70 miles. Everything waited on Cherbourg becoming minimally functional. August 12, 1944, 67 days after D-Day, HMS Latimer departed carrying the first operational HAIS cable. The laying took 10 hours, then disaster. A Royal Navy escort vessel, unaware of the pipeline's location, dropped anchor directly on the cable. The anchor dragged, severing the line before pumping even began. August 14th, HMS Sancroft laid a replacement, but when engineers attempted the final connection, the cable fouled in HMS Algerian's propeller. Destroyed again. August 27th, the first attempt to lay Hamill pipe using Conundrum 1 failed. 10 tons of barnacles had grown on the submerged portion, preventing rotation. The operation was abandoned. Each failure cost thousands of pounds and days of ship time, while Allied armies ashore faced intensifying fuel shortages. By late August, as American forces broke out of Normandy and raced across France, fuel supply became the critical constraint. September 22, 1944, 107 days after D-Day, marked the turning point. HMS Sancroft successfully laid HAIS cable from Shanklin to Cherbourg. Shore annexions completed. Pressure tests passed. At 14:23 hours, fuel began flowing beneath the English Channel for the first time. Initial delivery, 56,000 imperial gallons per day. Nowhere near the million gallons hoped for, but proof that Pluto worked. September 29th brought the first successful Hamill deployment. Conundrum 2, thoroughly cleaned, paid-out pipe from Isle of Wight to Cherbourg. Both pipelines delivered fuel for 3 days. October 3rd brought crushing disappointment. Both pipelines failed within hours. The HAIS cable ruptured at a coupling. The HAML pipe chafed against a rock formation on the channel floor until it ruptured. But October 3rd brought clarity. The failures revealed exactly what Pluto needed: better couplings and better surveys. More importantly, the strategic situation had changed. The Allies now controlled Boulogne, captured September 22, only 31 miles from Dungeness. October 10, 1944, HMS Sancroft laid the first pipeline of Operation Dumbo, from Dungeness to Boulogne. The crossing took 5 hours. The cable was tested, commissioned, and began delivering 56,000 imperial gallons per day almost immediately. The breakthrough came from persistence and adaptation. When Cherbourg proved difficult, they shifted to Boulogne. When couplings failed, engineers redesigned them. When pipes chafed, surveys identified safe routes. Through October and November, pipeline after pipeline was laid to Boulogne. 9 HAIS cables, 6 HAML pipes. Not all worked perfectly. HAML pipes proved more prone to failure, but redundancy was the plan. When one line failed, others continued. By January 1945, Dumbo reliably delivered 305 tons daily, approximately 80,000 imperial gallons, a tanker's worth of fuel every 3 days, without any ship sailing, any convoy forming, or any enemy opportunity to interdict supply. February 1945 brought major expansion. Pluto extended inland from Boulogne to Antwerp, Eindhoven, and eventually Emmerich on the Rhine. The submarine portion remained constant, but extension meant fuel reached front lines hundreds of miles inland. March 15, 1945, Dumbo surpassed 1 million imperial gallons daily. April 3, 1945 brought peak performance, 4,500 tons per day, approximately 1.2 million imperial gallons flowing beneath the channel to armies preparing to cross the Rhine. The transformation was complete. Pluto, which began as Hartley's proposal, which suffered months of failures, which seemed destined for the dustbin, had become the invisible artery sustaining Allied armies in the final drive to victory. The philosophy underlying Pluto emerged from Arthur Hartley's core principle: when conventional methods fail, change the parameters until physics permit success. The conventional pipeline paradigm circa 1942 was established. Large diameter pipes, 6 inches or greater, moved product at moderate pressure through moderate distances. For land-based pipelines, this worked. For submarine pipelines across 70 miles of open ocean with fierce tides, it was fantasy. Hartley's innovation was recognizing 3 constraints in direct opposition: diameter, pressure, and deployment speed. Increase diameter and pipe weight becomes unmanageable. Reduce pressure and fuel volume falls below requirements. Deploy slowly and tides destroy the work. The system had no solution unless you altered all 3 simultaneously. The HAIS cable was Hartley's answer. 3-inch diameter made weight manageable and allowed deployment by existing cable-laying ships, but 3 inches at conventional 50-100 psi would deliver only 10,000 gallons daily. Useless. Hartley's solution from Iran: dramatically increase pressure to 1,500 psi. At this pressure, 3 inches could move 56,000 gallons daily, equivalent to 50 supply trucks. The pressure requirement drove every design decision. The lead pipe had to be thick enough to contain pressure, yet flexible enough to coil. Steel tape reinforcement required 4 layers instead of 2 because tension at 1,500 psi would tear lighter construction apart. Wire armoring resisted both mechanical damage and enormous outward force. Material calculations were brutal. Lead has tensile strength of approximately 2,000 psi, barely adequate, minimal safety margin. Steel tape reinforcement provides circumferential reinforcement, but if gaps exist between layers, pressurized lead extrudes through like toothpaste. The solution: 4 tape layers added 50% to weight but provided necessary strength. Total HAIS construction: 3-inch lead pipe, asphalt impregnation, paper tape, 4 spiral steel wraps, wire armoring, jute bedding, outer wire serving, camouflaged canvas. Each mile weighed 46 tons, 31 tons lead, 15 tons steel. Manageable only because cable-laying ships deployed gradually while moving. Hamill philosophy differed fundamentally. Where HAIS prioritized flexibility, Hamill prioritized manufacturing speed. By mid-1943, HAIS production couldn't meet demand. The solution: simple steel pipe welded into long sections. Wall thickness 1.188 inches, thin enough to coil onto large drums, thick enough to contain 1,500 psi. The challenge was the drums. Steel pipe couldn't coil onto small drums without kinking. Solution: Conundrums. 30-foot diameter, large enough that 3-inch pipe could coil without exceeding material limits. But 30-foot drums loaded with 90 miles of pipe displaced 1,600 tons. Moving them required specialized tugs and enormous torque. The decision to pursue both technologies reflected pragmatic uncertainty. HAIS was proven but slow to manufacture. HAML was faster but less proven. Rather than commit fully, planners hedged, develop both, deploy whichever worked. The redundancy proved wise. HAIS cables were more reliable, not one broke after installation. HAML pipes failed more frequently, averaging one failure every 68 days. Pumping infrastructure reflected similar philosophy, over-designed for reliability, multiple pumps with massive capacity margins. If one failed, others compensated. If one pipeline ruptured, others continued. Redundancy pervaded every level. The disguise element added another layer. Pumping stations couldn't be obvious military targets, so they were hidden in plain sight. The Dungeness station as a gravel pit, the Isle of Wight shop selling ice cream while pumps drove fuel at 1,500 psi beneath. German intelligence knew the Allies had fuel supply, but never determined how. The cost was enormous. Pluto ultimately cost £4,428,000, approximately $300 million in today's dollars. Each conundrum cost £30,000. Each HAIS mile cost £3,000. But the alternative was worse. Fuel shortage at a critical moment could stop advances and ground aircraft. The design philosophy was simple: make impossible reliable. Accept the expensive, complex, redundant solution because the cheap, simple approach guaranteed failure. Build what nobody believes will work, prove it works, then scale it until it matters. By April 1945, this philosophy had proven correct. The fuel flowed, the armies advanced. The invisible pipeline sustained Allied victory. The operational history of Pluto reads as progression from technical curiosity to strategic necessity, measured in gallons delivered and battle sustained. August 12, 1944, first cable laid, immediately destroyed. Fuel delivered, 0. September 22, 1944, first successful cable operational. Fuel delivered, 56,000 imperial gallons per day, equivalent to 14 tanker trucks crossing invisibly while German intelligence searched frantically for the supply route. October 10, 1944, first Dumbo pipeline operational from Dungeness to Boulogne. Within days, multiple pipelines crossed. By late October, Dumbo delivered 220,000 imperial gallons daily, sufficient to fuel several armored divisions. The pattern through late 1944 was steady expansion. Each week brought new pipelines, HAIS cables from Latimer and Sancroft, HAML pipes from Conundrums. By December, 17 pipelines spanned from Dungeness to Boulogne. Not all worked perfectly. HAML pipes proved more prone to failure, averaging 68 days between repairs. But HAIS cables proved remarkably reliable. Not a single HAIS cable broke after successful deployment. January 1945, Dumbo delivered 80,000 imperial gallons daily. While modest compared to major tanker operations, this arrived regardless of weather or enemy action. Through January's harsh channel storms when tanker traffic was frequently suspended, Pluto continued operating. February 1945, strategic expansion. The inland pipeline extended from Boulogne toward front lines, reaching Antwerp, then Eindhoven, finally Emmerich on the Rhine. By early March, fuel pumped from England reached units preparing to cross the Rhine, over 400 miles from Dungeness. March 15, 1945, Dumbo surpassed 1 million imperial gallons daily. This vindicated skeptics who dismissed Pluto as expensive experimentation. 1 million gallons daily translated to 3,000 tons, enough to fuel several armored divisions plus supporting units. April 3, 1945, peak performance, 4,500 tons per day, approximately 1.2 million imperial gallons. This sustained a substantial portion of Allied fuel requirements for operations in Germany. The accumulated statistics became staggering. Between August 1944 and VE Day on May 8, 1945, Pluto delivered over 172 million imperial gallons. This represented approximately 8% of all petroleum supplied to Allied forces in Northwest Europe. While tankers still provided the majority, that 8% arrived with perfect reliability. No convoys to organize. No weather delays, no enemy interdiction opportunities. Consider what 172 million gallons meant practically. A Sherman tank consumed 150 gallons per 100 miles. Pluto delivered enough to drive every Sherman in Europe nearly 50,000 miles. A C-47 burned 150 gallons hourly. Pluto could have kept 1,100 C-47s flying continuously for 10 months. The human consequences were equally significant. Every gallon Pluto delivered didn't require tanker crews risking U-boats, beach personnel handling jerrycans under fire, or supply trucks vulnerable to air attack. Fuel arrived silently, continuously, invisibly, the safest possible method. Specific operations illustrated Pluto's value. During Operation Veritable and Blockbuster February-March 1945 offensives to clear the Rhineland, British and Canadian forces consumed fuel at unprecedented rates. Armored operations in mud required constant refueling. Pluto's steady supply helped sustain the offensive through its most fuel-intensive phase. The Rhine crossings in late March demanded enormous fuel stocks positioned forward. Pluto allowed this buildup without massive vulnerable convoys that Germans would have targeted. Fuel accumulated via pipeline, invisible to reconnaissance and immune to interdiction. But Pluto's impact extended beyond numbers. Its existence influenced German strategic calculations. German intelligence knew Allied fuel consumption rates and tanker capacity. They calculated that logistics should be vulnerable, yet fuel kept flowing faster than seemed possible. They never determined the truth, a pipeline network operating invisibly beneath the channel. This strategic uncertainty degraded German planning. If Allied logistics were better than calculated, attacks on supply lines would achieve less. Resources devoted to hunting non-existent tanker convoys were unavailable for other missions. Through April and early May 1945, as German resistance collapsed and Allied forces raced toward the Elbe, fuel supply became crucial for maintaining pace. Pluto delivered, steadily. On May 7th, Germany surrendered. On May 8th, VE Day celebrations erupted. On May 9th, Pluto continued pumping. Routine as clockwork, invisible as always. Final tally, 180 million imperial gallons delivered between August 1944 and August 7, 1945, when the system was shut down. 21 pipelines successfully deployed, over 1,000 personnel involved, 0 losses to enemy action, 0 interruptions longer than hours. The most reliable fuel supply system in military history. The complete picture emerges from comprehensive accounting of what was built and what it achieved. Pipeline production. HAIS cable manufactured totaled 710 nautical miles, 570 miles British-made from Siemens Brothers and Henley's, 140 miles from American manufacturers. Each mile required 31 tons of lead and 15 tons of steel. Hamill pipe production reached 550 kilometers from 2 Stewart's and Lloyd's factories at Tilbury, producing 16 kilometers daily at peak. Conundrums, 6 built at 30,000 pounds each 30 feet in diameter, displacing 1,600 tons when loaded with 90 miles of pipe. Vessel fleet at peak, HMS Holdfast, HMS Latimer, HMS Sancroft, HMS Algerian, HMS Persephone, plus 28 additional support vessels. Crew totaled over 1,000, commanded by Captain J.F. Hutchings. Inland pipeline, 990 miles across England, connecting West Coast ports to Channel Coast pumping stations, the government pipeline and storage system built specifically for Pluto. Cross-channel deployment, 17 operational pipelines to Boulogne, 9 HAIS, 6 Hamill, 2 smaller, plus additional lines to Cherbourg. Total channel floor mileage, 500 miles. Performance statistics. Peak delivery 4,500 tons per day, 1.2 million imperial gallons achieved April 1945. Total fuel delivered 180 million imperial gallons between August 1944 and August 1945. Percentage of total Allied fuel supplied 8%. To deliver 180 million gallons by tanker would have required over 4,000 coastal tanker voyages, each vulnerable to weather and enemy action. Pluto eliminated this entirely, operating with no losses to enemy action and no weather interruptions longer than hours. Cost accounting. Total expenditure, £4,428,000, approximately $300 million today. Breakdown. Pipelines, £2,100,000, conundrums and vessels, £800,000, pumping stations, £900,000, inland extensions, £450,000, operations, £178,000. Salvage operation between 1946 and 1949 recovered over 85% of deployed pipeline, 22,000 tons of lead and 3,300 tons of steel. Salvage value exceeded recovery costs. Materials sold for £400,000, more than covering £280,000 spent on salvage. Awards. Arthur Hartley received £9,000 tax-free, B.J. Ellis £5,000, plus Hartley received CBE in 1944 and American Medal of Freedom in 1946. General Eisenhower described Pluto as second in daring only to the Mulberry Harbors. Personnel, over 1,000 served in Pluto operations. Zero loss to enemy action during deployment, remarkable given dangerous channel conditions and constant German air activity. Comparative analysis, to match Pluto's 4,500 tons daily would require 14 tankers in continuous rotation with crews of 30 to 40 each, total 420 to 560 personnel versus 50 actually operating Pluto pumping stations. The manpower savings alone justified investment. Vulnerability comparison. Tankers were large, slow, visible targets. Pluto was invisible, invulnerable, and immune to weather that grounded tanker traffic. The 8% arriving via pipeline was the 8% that couldn't be stopped, the foundation allowing the remaining 92% to be planned with confidence. Post-war technical legacy. Pluto pioneered submarine pipeline deployment techniques that revolutionized offshore oil production. Methods for winding pipe onto large drums and deploying under tow became standard in North Sea oil development 2 decades later. The final accounting shows a project that cost £4.4 million, employed 1,000 personnel, deployed 500 miles of pipeline, and delivered 8% of Allied fuel with 100% reliability. Not the war-winning weapon that propaganda might claim, but an essential component that worked precisely when and how it was needed. April 15, 1947. 5 years after Arthur Hartley proposed his impossible pipeline, Hartley stands on Dungeness Beach watching Empire Ridley, formerly HMS Latimer, recover the last accessible Hamill pipe from the channel floor. The pipe emerges, still intact, still capable of containing 1,500 psi despite 2 years submerged and unused. Hartley is 58 now, retired from Anglo-Iranian, working as a consulting engineer. The war is over. The pipeline that experts declared impossible has been proven, operated, and now carefully disassembled. Pluto appears in few newspapers. No monuments commemorate it. The pumping stations are being converted to residential use, bungalows that locals will inhabit, never knowing they once contained pumps driving fuel at pressures that could crush a human skull. The historical judgment seems anticlimactic. Pluto delivered 180 million gallons, impressive in absolute terms, modest as a percentage. It cost £4.4 million. It employed 1,000 personnel. By pure numbers, a supporting player, not a star. But Hartley knows something statistics miss. Every gallon Pluto delivered arrived with perfect certainty. In mechanized warfare, certainty is the rarest commodity. Weather grounds tankers, U-boats sink convoys, air attacks destroy fuel dumps. 1,000 variables interrupt traditional logistics. Pluto was immune to all of them. Storms could rage, the fuel flowed. Enemy aircraft could patrol, seeing nothing. U-boats could hunt convoys that never sailed. The visible supply lines drew enemy attention, but underneath, literally underneath the channel floor, the invisible artery pumped relentlessly. The strategic insight Mountbatten grasped in 1942 was that modern warfare is won not just by combat power, but by sustained logistics. An armored division without fuel is stationary weight. A fighter wing without aviation spirit is grounded scrap. Pluto guaranteed that fuel would be there when needed, regardless of circumstances. This guarantee changed Allied planning. Knowing minimum fuel supply was absolutely reliable allowed more aggressive operational tempo. Knowing weather delays wouldn't create cascading shortages allowed attacks through poor conditions. Knowing the enemy couldn't interdict the supply line allowed concentration on actual combat rather than logistics defense. Pluto represented something beyond logistics, proof that the physical world could be bent to necessity when engineering met audacity. The experts in April 1942 weren't wrong about conventional methods being impossible. They were simply thinking conventionally. Hartley's insight was that changing parameters, smaller diameter, higher pressure, continuous deployment, transformed impossible into merely very difficult. Throughout the war, similar innovations emerged when necessity confronted impossibility. Mulberry harbors creating ports where none existed, cavity magnetrons enabling radar-directed night fighting, code-breaking reading signals thought unbreakable. Each represented the same philosophy: refuse to accept impossibility, then engineer a solution anyway. Pluto's contribution to Allied victory is ultimately unquantifiable. The 180 million gallons can be counted. The 8% can be calculated. But how do you measure the value of certainty? How do you calculate worth of a supply line the enemy cannot attack? How do you quantify strategic confidence that comes from knowing fuel will be there when needed? By VE Day, Pluto had become routine. Pumping stations operated on schedule. Fuel flowed. The system that seemed miraculous in 1942 was ordinary by 1945. Perhaps that mundane reliability is the highest praise. The impossible became routine, became indispensable. Hartley watches Empire Ridley complete recovery and begin the slow return to port. Soon, nothing visible will remain. The pumping stations will become houses. The Conundrums will be scrapped. The ships will return to commercial service. Future generations will know Pluto, if at all, as a footnote. But standing on Dungeness shingle with channel wind cold against his face, Hartley knows the truth. Pluto succeeded not because it delivered the most fuel, but because it delivered fuel with perfect reliability when that reliability mattered most. It succeeded because it changed what was possible, expanding engineering boundaries to meet strategic demands. It succeeded because dedicated professionals refused to accept expert consensus that something was impossible and instead made it real. The pipeline beneath the channel proved that modern warfare requires more than courage and tactics. It requires logistics robust enough to sustain combat regardless of circumstances. It requires engineering sophisticated enough to overcome physics rather than surrender to it. And it requires institutional confidence to commit enormous resources to projects that seem impossible, trusting that skilled engineers, given adequate support, can achieve what conventional wisdom says they cannot. That confidence was vindicated. The fuel flowed, the armies advanced, the war was won. And beneath it all, silent and invisible, Arthur Hartley's impossible pipeline delivered victory one pressure-tested gallon at a time. The examination of Pluto's legacy reveals not a weapon, but a principle, that the sinews of war, supply, logistics, infrastructure, matter as much as the claws, that reliability beats capacity when reliability is what strategy requires, that engineering creativity can achieve strategic effects as decisive as battlefield heroics, and that sometimes the most important contributions to victory are the ones nobody sees, flowing silently beneath the surface, sustaining everything above. Pluto was not poorly designed. It was brilliantly designed to achieve a specific goal: deliver fuel across the channel with absolute reliability regardless of enemy action or weather. That goal was achieved. The pipelines delivered, the armies advanced, and in achieving that unglamorous, invisible, technically complex goal, Pluto helped win a war.